Symmetric and asymmetric key cryptography. In this video, we are going to see about symmetric and asymmetric key cryptography. Cryptographic techniques are typically divided into two generic types, symmetric key and asymmetric key. Symmetric cryptography relies on a shared secret key K between two parties to enable secure communication. Asymmetric cryptography employs two different keys, a private key D and a public key E. The public key E is used for encryption and can be published. The private key D is used for decryption. Asymmetric key cryptography. Two keys are used in asymmetric cipher, for example, RSA, a public and a private one. The public one is available for everyone, but the private one is known only by the owner. When the message is encrypted with a public key, only the corresponding private key can decrypt it. Moreover, the private key cannot be learned from the public one. Asymmetric cipher solves the problem of secure key distribution. Alice takes Bob's public key and uses it to encrypt the session key. Only Bob can then decrypt the encrypted session key because he is the only one who knows the corresponding private key. Asymmetric ciphers are quite slow when compared with the symmetric ones, which is why asymmetric ciphers are used only to securely distribute the key. Then, Alice and Bob can use symmetric cipher and the session key to make the communication confidential. Use of an asymmetric cipher also solves the scalability problem. Everyone will need only one public key and one private key to communicate with other people. Symmetric key cryptography. Let us assume that Alice wants to talk to Bob. She wants to keep the message secret. Bob is the only one who should be able to read the message. The message is confidential, so Alice uses a key to encrypt the message. The original message is called a plain text, while the encrypted message is called a ciphertext. The ciphertext is sent to Bob, who knows the key and uses the same symmetric cipher, that is, for example, AES or 3DES. Thus, Bob is able to decrypt the message. Alice and Bob share the key, which is called symmetric. There are the only ones who know the key and no one else is able to read the encrypted message. This way, confidentiality is achieved. What is RSA key management? In this video, we are going to see about what is RSA key management. RSA is an Internet encryption and authentication system developed in 1977 by Ron Rivest, Adi Shamir, and Leonard Edelman. RSA is one of the first practicable public key crypto systems and is widely used for secure data transmission. In such a crypto system, the encryption key is public and differs from the decryption key, which is kept secret. In RSA, this asymmetry is based on the practical difficulty of factoring the product of two large prime numbers, the factoring problem. A user of RSA creates and then publishes a public key based on the two large prime numbers along with an auxiliary value. The prime numbers must be kept secret. Anyone can use the public key to encrypt a message, but with currently published methods, if the public key is large enough, only someone with knowledge of the prime numbers can feasibly decode the message. Breaking RSA encryption is known as the RSA problem. Whether it is hard as the factoring problem remains an open question. Attacks on RSA. In this video, we are going to see about attacks on RSA. 4 possible approaches for attacking the RSA algorithm are brute force. This involves trying all possible private keys. Mathematical attacks. There are several approaches, all equivalent in effort to factoring the product of two primes. Timing attacks. These depend on the running time of the decryption algorithm. Chosen ciphertext attack. This type of attack exploits properties of the RSA algorithm. Brute force attack. The defense against the brute force approach is the same for RSA as for other crypto systems, namely to use a large key space. Thus, the larger the number of bits in D, the better. However, because the calculations involved, both in key generation and in encryption or decryption, are complex, the larger the size of the key, the slower the system will run. Mathematical attacks. We can identify 3 approaches for attacking RSA mathematically. Factor n into its 2 prime factors. This enables the calculation of phi of n is equal to p minus 1 into q minus 1, which in turn enables determination of d into k e inverse of mod phi of n. Determine phi of n directly without first determining p and q. Again, this enables determination of d into k e inverse of mod phi of n. Determine d directly without first determining phi of n. Most discussions of the cryptanalysis of RSA have focused on the task of factoring n into its 2 prime factors. Determining phi of n given n is equivalent to factoring n of RIBE96. With presently known algorithms, determining d given e and n appears to be at least as time-consuming as the factoring problem. Hence, we can use factoring performance as a benchmark against which to evaluate the security of RSA. For a large n with large prime factors, factoring is a hard problem, but it is not as hard as it used to be. Timing attacks. If one needed it, another lesson about how difficult it is to access the security of a cryptographic algorithm, the appearance of timing attacks provides a stunning one. Paul Coker, a cryptographic consultant, demonstrated that a snooper can determine a private key by keeping track of how long a computer takes to decipher messages. Timing attacks are applicable not just to RSA but to other public key cryptography systems. A timing attack is somewhat analogous to a burglar guessing the combination of a safe by observing how long it takes for someone to turn the dial from number to number. We can explain the attack using the modular exponentiation algorithm, but the attack can be adapted to work with any implementation that does not run in fixed time. In this algorithm, modular exponentiation is accomplished bit by bit, with one modular multiplication performed at each iteration and an additional modular multiplication performed for each one bit. Suppose the target system uses a modular multiplication function that is very fast in almost all cases, but in a few cases takes much more time than an entire average modular exponentiation. The attack proceeds bit by bit, starting with the leftmost bit bk. Suppose that the first j bits are known. To obtain the entire exponent, start with j is equal to 0 and repeat the attack until the entire exponent is known. For a given ciphertext, the attacker can complete the first j iterations of the for loop. The operation of the subsequent step depends on the unknown exponent bit. If the bit is set, d is equivalent to d into a mod n will be executed. For a few values of a and d, the modular multiplication will be extremely slow and the attacker knows which these are. Therefore, if the observed time to execute the decryption algorithm is always slow, when this particular iteration is slow with a 1 bit, then this bit is assumed to be 1. If a number of observed execution times form the entire algorithm of fast, then this bit is assumed to be 0. Although the timing attack is a serious threat, there are simple countermeasures that can be used, including the following: constant exponentiation time, random delay, blinding. Constant exponentiation time. Ensure that all exponentiations take the amount of time before returning a result. This is a simple fix but does degrade performance. Random delay. Better performance could be achieved by adding a random delay to the exponentiation algorithm to confuse the timing attack. Coker points out that if defenders don't add enough noise, the attackers could still succeed by collecting additional measurements to compensate for the random delays. Blinding. Multiply the ciphertext by a random number before performing exponentiation. This process prevents the attacker from knowing what ciphertext bits are being processed inside the computer and therefore prevents the bit-by-bit analysis essential to the timing attack. Chosen ciphertext attack. The basic RSA algorithm is vulnerable to a chosen ciphertext attack CCA. CCA is defined as an attack in which the adversary chooses a number of ciphertexts and is then given the corresponding plaintext decrypted with the target's private key. Thus, the adversary could select a plaintext, encrypt it with the target's public key, and then be able to get the plaintext back by having it decrypted with a private key. Clearly, this provides the adversary with no new information. Instead, the adversary exploits the properties of RSA and selects blocks of data that, when processed using the target's private key, yield information needed for cryptanalysis. Example of RSA. In this video, we are going to see about example of RSA. Here is an example of RSA scheme in action. I have chosen primes that are large enough to be interesting but small enough that you can do all of the arithmetic with a pen, paper, and calculator. Key generation. P is equal to 31, Q is equal to 23, chosen at random. N is equal to 31 into 23 is equal to 713. R is equal to 30 into 22, which is equal to 660. E is equal to 223, chosen at random. 660 is equal to 223 into 2 plus 214. 223 is equal to 214 into 1 plus 9. 214 is equal to 9 into 23 plus 7. 9 is equal to 7 into 1 plus 2. 7 is equal to 2 into 3 plus 1. 1 is equal to 7 minus 3 of 2. 1 is equal to 7 minus 3 of 9 minus 7, which is equal to 4 of 7 minus 3 of 9. 1 is equal to 4 into 214 minus 9 into 23 minus 3 into 9 is equal to 4 into 214 minus 95 into 9. 1 is equal to 4 into 214 minus 95 into 223 minus 214 is equal to 99 into 214 minus 95 into 223. 1 is equal to 99 into 660 minus 2 into 223 minus 95 into 223. 1 is equal to 99 into 660 minus 293 into 223. So, the inverse of 223 mod 660 is equal to minus 293 is equal to 367. D is equal to 367, computed using Euclid's algorithm as below. Bob's private key is equal to 367. Bob's public key is equal to 223, 713. Encryption. Alice wishes to send Bob the message M is equal to 439. She computes C is equal to 439 to the power 223 mod 713, which is equal to 284. Alice sends the ciphertext 284 to Bob. Decryption. Bob receives the ciphertext 284 from Alice. He computes 284 par 367 mod 713 is equal to 439. He knows the message is 439. Difference between symmetric and asymmetric. In this video, we are going to learn about difference between symmetric and asymmetric. Symmetric cryptography. Symmetric cryptography uses the same secret keys to encrypt and decrypt its data. Asymmetric cryptography. Asymmetric uses both a public and private key. Symmetric cryptography. Symmetric requires that the secret key be known by the party encrypting the data and the party decrypting the data. Asymmetric cryptography. Asymmetric allows for distribution of your public key to anyone with which they can encrypt the data they want to send securely, and then it can only be decoded by the person having the private key. Symmetric cryptography. Symmetric encryption is faster to encrypt large amount of data. Asymmetric cryptography. Asymmetric encryption is 1000 times slower than symmetric key to encrypt a data. Symmetric cryptography. Symmetric key encryption can be extremely secure. Asymmetric cryptography. Whereas asymmetric key is lower secure than symmetric key. Symmetric cryptography. The biggest problem with symmetric key encryption is sharing of data is difficult. Asymmetric cryptography. Sharing of data in asymmetric key encryption is comparably easy than symmetric key encryption. Introduction to key management. In this video, we are going to see about Introduction to key management. The key management is a set of techniques and procedures supporting the establishment and maintenance of keying relationships between authorized parties. A keying relationship is the state where communicating entities shares the common data that is keying material to facilitate cryptography techniques. The data includes dealing with the generation, exchange, storage, use, and replacement of keys. One of the major roles of public key encryption has been to address the problem of key distribution. There are two distinct aspects to the uses of public key encryptions. They are distribution of public key, the use of public key encryption to distribute secret keys, symmetric key distribution. Distribution of public key. In this video, we are going to see about distribution of public key. A few techniques have been proposed for the distribution of public keys. Nearly all of these proposals can be grouped into the following general schemes: public announcement, publicly available directory, public key authority, public key certificates. Public announcement. Apparently, the point of public key encryption is that the key should be public. Thus, if there is some broadly accepted public key algorithm such as RSA, any participant can send public key to any other participant or broadcast the key to the community at wide area. Although this approach is convenient, it has a major weakness. Anyone can forge such a public announcement. That is, some user could pretend to be user A and send a public key to another participant or broadcast such a public key. Publicly available directory. Publicly available directory achieves greater security by registering keys with a public directory. Maintenance and distribution of the public directory would have to be the responsibility of some trusted entity or organization. Such a scheme would include the following elements. The authority maintains a directory with a name, public key, entry for each participant. Each participant registers a public key with the directory authority. Registration would have to be in person or by some form of secure authenticated communication. A participant may replace the existing key with a new one at any time. Periodically, the authority publishes the entire directory or updates to the directory. Participants could also access the directory electronically, so the secure and authenticated communication to the participant is mandatory. This proposal is clearly more secure than individual public announcements but still have vulnerabilities. If an opponent succeeds in obtaining or computing the private key of the directory or authority, the opponent could authoritatively pass out counterfeit public keys. Public key authority. Stronger security for public key distribution can be achieved by providing strong control over the distribution of public keys from the directory. The scenario for public key authority is shown. A sends a time-stamped message to the public key authority containing a request for the current public key of B. The authority responds with a message that is encrypted using the authority's private key. Thus, A is able to decrypt the message using the author public key. Therefore, A is assured that the message originated with the authority. A stores B's public key and uses it to encrypt a message to B containing an identifier of A of ID and unknowns N1, which is used to identify this transaction uniquely. B retrieves A's public key from the authority in the same manner as A retrieved B's public key. At this point, public keys have been securely delivered to A and B, and they may begin their protected exchange. However, two additional steps are desirable. B sends a message to A encrypted with KU and containing A's nonce N as well as new nonce created by B and J. Because only B could have decrypted message 3, the presence of N in message 6 assures A that the correspondent is B. A returns N to encrypt using B's public key to assure B that its correspondent is A. Therefore, the total of 7 messages are required for this type of authority. Public key certificates. Public key certificates allow key exchange without real-time access to public key authority. Each certificate containing a public key and other information is created by a certificate authority and is given to the participant with a matching private key. A participant conveys its key information to another by transmitting its certificate. Other participants can verify that the certificate was created by the authority. 4 requirements can be placed on this particular scheme. Any participant can read a certificate to determine the name and public key of the certificate's owner. Any participant can verify that the certificate originated from the certificate authority and is not counterfeit. Only the certificate authority can create and update certificates. Any participant can verify the currency of the certificate. X.509 Authentication Service. The ITUT recommendation X.509 Directory Authentication Service is a part of the X.500 series of recommendations that define a directory service. The directory is in effect a server or distributed set of servers that maintains a database of information about users. X.509 defines a framework for the provision of authentication services by the X.500 directory to its users. The directory may serve as a repository of public certificates. Each certificate contains a public key of a user and is signed with a private key of a trusted certificate authority (CA). X.509 is based on the use of public key cryptography and digital signatures, for example, RSA and different hash functions such as MD5, etc. X.509 was initially issued in 1988. The standard was subsequently revised to address some of the security concerns. A revised recommendation was issued in 1993. A third version was issued in 1995 and revised in 2000. The user certificates, which are at the heart of X.509, are assumed to be created by some trusted certificate authority (CA) and placed in the directory by the CA or by the user. The directory server itself is not responsible for the creation of the public keys or for the certification function. It merely provides an easily accessible location for users to obtain certificates. Any user with access to the public key of the CA can recover the user public key that was certified. No party other than the CA can modify the directory. Public key distribution of secret key. In this video, we are going to see about public key distribution of secret key. Public key distribution of secret key. Once public keys have been distributed or have become accessible, secure communication that thwarts eavesdropping, tampering, or both is possible. However, few users will wish to make exclusive use of public key encryption for communications because of the relatively slow data rates that can be achieved. Simple secret key distribution. An extremely simple scheme put forward by Ralph Merkle. If A wishes to communicate with B, the following procedure is employed. A generates a public or private key pair, that is KUA, KRA, and transmits a message to B consisting of KUA and an identifier of A, IDA. B generates a secret key, KS, and transmits it to A, encrypted with A's public key. A computes DKRA of EKUA of KS to recover the secret key. Since only A can decrypt the message, only A and B will know the identity of KS. A discards KUA and KRA and B discards KUA. A and B can now securely communicate encryption and the session key is KS. At the completion of the exchange, both A and B discard KS. Despite its simplicity, this is an attractive protocol. No keys exist before the start of the communication and none exist after the completion of communication. Thus, the risk of compromise of the keys is minimal. At the same time, the communication is secure from eavesdropping. The protocol is vulnerable to an active attack. If an opponent E has control of the intervening communications channel, then he can compromise the communications in the following way without being detected. A generates a public or private key pair, that is KUA, KRA, and transmits a message intended for B consisting of KUA and identifier of A, IDA. E intercepts the message, creates its own public or private key pair KUE, KRE, and transmits KUE exactly divides IDA to B. B generates a secret key KS and transmits EKUE of KS. E intercepts the message and learns KS by computing DKRE of EKUE of KS. E transmits EKUA of KS to A. The result is that both A and B know KS and are unaware that KS has also been revealed to E. A and B can now exchange messages using KS. E no longer actively interferes with the communications channel but simply eavesdrops. Knowing KS, E can decrypt all messages and both A and B are unaware of the problem. Thus, this simple protocol is only useful in an environment where the only threat is eavesdropping. Secret key distribution with confidentiality and authentication. Protection against both active and passive attacks. For this example, it is assumed that A and B have exchanged public keys by one of the schemes described earlier in this section. A uses B's public key to encrypt a message to B containing an identifier of A, IDA, and a nonce N1, which is used to uniquely identify this transaction. B sends a message to A encrypted with KUA and containing A's nonce N1 as well as a new nonce generated by B, N2. Since only B could have decrypted message 1, the presence of N1 in message 2 assures A that the correspondent is B. A returns N2, encrypted using B's public key to assure B that its correspondent is A. A selects a secret key KS and sends M is equal to EKUB of EKRA of KS to B. Encryption of this message with B's public key ensures that only B can read it Encryption with A's private key ensures that only A could have sent it. B computes DKUA of DKRB of M to recover the secret key. Symmetric key distribution. In this video, we are going to see about symmetric key distribution. In symmetric key cryptography, both parties must possess a secret key which they must exchange prior to using any encryption. Distribution of secret keys has been problematic until recently because it involved face-to-face meeting, use of a trusted courier, or sending the key through an existing encryption channel. The first two are often impractical and always unsafe, while the third depends on the security of a previous key exchange. In public key cryptography, the key distribution of public keys is done through public key servers. When a person creates a key pair, he keeps one key private and the other public key is uploaded to a server where it can be accessed by anyone to send the user a private encrypted message. Possibilities in symmetric key protocol. A physically delivers key to B. Third party C can physically deliver key to A and B. If A and B already have a key, can securely transmit new key to each other, encrypted with old key. If A and B have secure connection with third party C, C can securely send keys to A and B. Diffie-Hellman key exchange. In this video, we are going to see about Diffie-Hellman key exchange. Diffie-Hellman key exchange DH to the power NB1 is a specific method of exchanging keys. It is one of the earliest practical examples of key exchange implemented within the field of cryptography. The Diffie-Hellman key exchange method allows two parties that have no prior knowledge of each other to jointly establish a shared secret key over an insecure communication channel. This key can then be used to encrypt subsequent communications using asymmetric key cipher. It is a type of key exchange. Process of Diffie-Hellman algorithm. The Diffie-Hellman algorithm depends for its effectiveness on the difficulty of computing discrete logarithms. Briefly, we can define the discrete logarithm in the following way. A mod p, a square mod p, and so on up to a power n minus 1 mod p. First, we define a primitive root of a prime number p as one whose powers generate all the integers from 1 to p minus 1. That is, if a is a primitive root of the prime number p, then the numbers b is equal to a power I mod p, where 0 less than or equal to I greater than or equal to p minus 1. For any integer b and a primitive root a of prime number p, one can find a unique exponent I such that the exponent I is referred to as the discrete logarithm or index of b for the base a mod p. This value is denoted as ind a, p of b. Suppose the users A and B wish to exchange a key. User A selects a random integer xa less than q and computes ya is equal to a power xa mod q. Similarly, user B independently selects a random integer xb is less than q and computes yb is equal to a power xn mod q. Each side keeps the x value private and makes the y value available publicly to the other side. User A computes the key as k is equal to yb to the power xa mod q and user B computes the key as k is equal to ya to the power xb mod q. These two calculations produce identical results. K is equal to yb to the power xb mod q. A power xb mod q to the power xa mod q. A power xb to the whole power xa mod q. A power xb into xa mod q. A power xa to the power of xb mod q. A power xa mod q to the power xb mod q. Ya to the power xb mod q. Thus, the two sides have exchanged a secret key. Furthermore, because xa and xb are private, an opponent only has the following ingredients to work with q, a, ya and yb. Thus, the opponent is forced to take a discrete logarithm to determine the key. For example, attacking the secret key of user B, the opponent must compute xb is equal to ind a, q of yb. The opponent can then calculate the key k in the same manner as user B calculates it. The security of the Diffie-Hellman key exchange lies in the fact that while it is relatively easy to calculate exponentials modulo a prime, it is very difficult to calculate discrete logarithms. For large primes, the latter task is considered infeasible. Example of Diffie-Hellman key exchange. Key exchange is based on the use of the prime number q is equal to 97 and a primitive root of 97. In this case, a is equal to 5. Select a and b secret keys. Xa is equal to 36 and xb is equal to 58 respectively. Each computes its public key. Ya is equal to 5 power 36 is equal to 50 mod 97. Yb is equal to 5 power 58 is equal to 44 mod 97. After they exchange public keys, each can compute the common secret key. K is equal to yb power xa mod 97 is equal to 44 power 36 is equal to 75 mod 97. K is equal to ya power xb mod 97 is equal to 50 power 58 is equal to 75 mod 97. Attacks on Diffie-Hellman. In this video, we are going to see about attacks on Diffie-Hellman. In attacks on Diffie-Hellman, a problem is left which the party knows whom it shared the secret with. This can be exploited by a man-in-the-middle attack. The attacker M inserts itself on the communications path between A and B, replies to A when A initiates a protocol run, and at the same time starts a protocol run with B where M pretends to be A. Principals A and B might believe they have established a shared key. In fact, M shares key G power XU with A and key G power YV with B, and can read all traffic between A and B while acting as a relay. What is RSA? In this video, we are going to see about what is RSA. The RSA algorithm, named after Ron Rivest, Adi Shamir, and Leonard Adleman, is based on a property of positive integers. RSA encryption is a public key encryption technology developed by RSA Data Security. The RSA algorithm is based on the complexity in factoring very large numbers. Based on this principle, the RSA encryption algorithm uses prime factorization as the corner door for encryption. RSA key takes a huge amount of time and processing power. RSA is the standard encryption method for important data, especially data that is transmitted over the internet. There are many applications for RSA, but in practice, it is most often used for encryption of small pieces of data, especially for key transport, digital signatures, which is discussed in earlier example for digital certificates on the internet. Encryption and decryption of RSA. RSA encryption and decryption is done in the integer ring Zn, and modular computations play a central role. RSA encrypts plain text X, where we consider the hit string representing X to be an element in Zn is equal to set 0, 1 and so on up to n-1. As a consequence, the binary value of the plain text X must be less than it. The same holds for the ciphertext. Encryption with the public key and decryption with the private key are as shown below. RSA encryption. Given the public key n, is equal to kpub and the plain text X, the encryption function is y is equal to e kpub of X is congruent to x bar e mod n, where x, y belongs to Zn. RSA decryption. Given the private key d is equal to kpr and the ciphertext y, the decryption function is x is equal to dkpr of y is congruent to y power d mod n, where x, y belongs to Zn. In practice, x, y, n and d are very long numbers, usually 1024-bit long or more. The value e is sometimes referred to as encryption exponent or public exponent, and the private key d is sometimes called decryption exponent or private exponent. If user A wants to send an encrypted message to user B, A needs to have his public key of n, e and B decrypts with his private key d. Even without knowing more details, we can already state a few requirements for the RSA cryptosystem. Since an attacker has access to the public key, it must be computationally infeasible to determine the private key d given the public key values e and n. Since X is only unique up to the size of the modulus n, we cannot encrypt more than L bits with one RSA encryption, where I is the bit length of n. It should be relatively easy to calculate x per e mod n, that is to encrypt, and y per d mod n, that is to decrypt. This means we need a method for fast exponentiation with very long numbers. For a given n, there should be many private key or public key pairs, otherwise an attacker might be able to perform a brute force attack. It turns out that this requirement is easy to satisfy. Attacks on RSA. In this video, we are going to see about attacks on RSA. The RSA function is an example of a one-way trapdoor function. It is not known to be easily invertible without the trapdoor d. General attacks on RSA involve trying to compute d or some other way to get to m. RSA security depends on the computation to be unreasonable for the factoring of n and computing the e-truths modulo n. There are four possible approaches to attack the RSA algorithm. They are brute force, mathematical attacks, timing attacks, chosen ciphertext attacks. Brute force. This involves trying all possible private keys. Mathematical attacks. There are several approaches, all equivalent in effort to factoring the product of two primes. Timing attacks. These depend on the running time of the decryption algorithm. Chosen ciphertext attacks. This type of attack exploits properties of the RSA algorithm. Brute force attack. Brute force attack try every combination of numbers, letters, and special characters until the password is discovered. Many password cracking utilities let us specify such testing criteria as the characters and password length to try. A brute force test can take quite a while depending on the number of accounts, their associated password complexities, and the speed of the computer that is running the cracking software. Symmetric cipher. For a symmetric cipher, longer keys protect against brute force attacks. Each extra bit in the key doubles the number of possible keys and therefore doubles the work a brute force attack must do. With an n-bit key, there are 2 n possible keys. On average, a brute force attack must test half of them, performing 2n-1 encryptions to find the key. A large enough key makes any brute force attack wildly impractical. Public key system. For public key systems, the relation between key size and security is more complex. Here an attacker has the public key and that is mathematically related to the private key. He need not try all possible keys, only solve a math problem. For example, to break a 256-bit key used in the RSA crypto system, he has to factor a 256-bit number. This is not easy, but it is far better for the attacker than a brute force search. Mathematical attack. In this video, we are going to see about mathematical attack. Mathematical attacks focus on attacking the underlying structure of RSA function. The first intuitive attack is the attempt to factor the modulus n. Because knowing the factorization of n, one may easily obtain m of n, from which d can be determined by d is equal to 1 by e mod m of n. Problems and difficulties in mathematical attacks. With phi of n and n, we can read any message encrypted, so our problem is equivalent to the problem of prime factorization. Prime factorization requires splitting an integer into factors that are prime numbers, and every integer has a unique prime factorization. Multiplying two prime integers together is easy, but as far as we know, factoring the product is much more difficult. Factoring algorithm. In factoring algorithm, there are 3 methods involved to express n difference in prime numbers. Algorithm of Fermat, algorithm on Euler, Pollard's row method. Algorithm of Fermat. This method is based on the formula of difference of two squares. X square minus y square is equal to x minus y into x plus y. In case of the particular modulus n in RSA, n is equal to p into q, where p, q are 2 primes. We can express n as n is equal to p plus q by 2 the whole square minus p minus q by 2 whole square. Let k the smallest positive integer so that k square is greater than n. Consider now k square minus n. If a number h, such as k square minus n is equal to h square, then n is equal to k plus h into k minus h. As n can only factor as p into q, so we will be sure k plus h and k minus h must be 2 prime numbers. If not the case, consider eventually to find g, such as k plus g the whole square minus n is equal to h square is a square. So n can be factored as k plus g plus h into k plus g minus h. Algorithm on Euler. The idea of this method is that to express a number n as the sum of two squares in two different ways with factor n. N is equal to a square plus b square, which is equal to c square plus d square. A minus C into A plus C is equal to D minus B into D plus B. Let K is equal to GCD of A minus C comma D minus B. So A minus C is equal to Km, D minus B is equal to Kh. And as GCD of M comma H is equal to 1, so we must have B plus D is divisible by M. We have B plus D is equal to M into N. Consequently, A plus C is equal to H into N. We have 4 equations there. A minus C is equal to K into M. A plus C is equal to H into N. D minus B is equal to K into H. D plus B is equal to M into N. We deduce A is equal to K into M plus H into N divided by 2. B is equal to M into N minus K into H divided by 2. N is equal to K into M plus H into N by 2 the whole square plus M into N minus K into H divided by 2 the whole square. N is equal to K square into M square plus H square into N square plus 2KMHN plus M square into N square plus K square into H square minus 2KMHN the whole divided by 4. N is equal to K square plus N square into M square plus H square into K square plus N square the whole divided by 4. N is equal to K square plus N square into M square plus H square the whole divided by 4. Euler's factorization method is more effective than Fermat's for integers of which factors are not close, and actually much more efficient than trial division if one can find representation of numbers as sums of two squares reasonably easily. The disadvantages of Euler's factorization method is that it cannot be applied to factoring any integer with any prime factor of the form 4k plus 3 occurring to an odd power in its prime factorization, as such a number can never be the sum of two squares. Pollard's row method. The principle of Pollard's row method is to pick a random number A, pick another random number B, see if the greatest common divisor of A minus B and N is greater than 1. If not, pick another random number C. Check the greatest common divisor of C minus B and N. If that is not greater than 1, check the greatest common divisor of C minus A and N. If that does not work, pick another random number D. Check D minus C, D minus B and D minus A. Timing attack. In this video, we are going to see about timing attack. A timing attack is an example of an attack that exploits the data-dependent behavioral characteristics of the implementation of an algorithm rather than the mathematical properties of the algorithm itself. Many cryptographic algorithms can be implemented or masked by a proxy in a way that reduces or eliminates data-dependent timing information. Consider an implementation in which every call to a subroutine always returns in exactly x seconds, where x is the maximum time it ever takes to execute that routine on every possible authorized input. In such an implementation, the timing of the algorithm leaks no information about the data supplied to that invocation. The downside of this approach is that the time to execute many invocations increases from the average performance of the function to the worst-case performance of the function. Timing attacks are practical in many cases. Timing attacks can be applied to any algorithm that has data-dependent timing variation. Software run on a CPU with a data cache will exhibit data-dependent timing variations as a result of memory looks into the cache. Some operations such as multiplication may have varied execution time depending on the inputs. Finding secrets through timing information may be significantly easier than using cryptanalysis of known plaintext ciphertext pairs. Sometimes timing information is combined with cryptanalysis to improve the rate of information leakage. Chosen ciphertext attack. In this video, we are going to see about chosen ciphertext attack. The basic RSA algorithm is vulnerable to a chosen ciphertext attack CCA. CCA is defined as an attack in which the adversary chooses a number of ciphertexts and is then given the corresponding plaintext decrypted with the target's private key. Thus, the adversary could select a plaintext, encrypt it with the target's public key, and then be able to get the plaintext back by having it decrypted with a private key. Clearly, this provides the adversary with no new information. Instead, the adversary exploits properties of RSA and selects blocks of data that, when processed using the target's private key, yield information needed for cryptanalysis. A simple example of a CCA against RSA takes advantage of the following property of RSA. E of PU, M1 into E of PU, M2 is equal to E of PU, M1 into M2. We can decrypt C is equal to ME mod N using a CCA as follows. Compute X is equal to C into 2E mod N. Submit X as a chosen ciphertext and receive back Y is equal to XD mod N. But now, note that is equal to 2M into E mod N is equal to ME mod N into 2E mod N. X is equal to C mod N into 2E mod N. El-Gamal. In this video, we are going to see about El-Gamal. In cryptography, the El-Gamal encryption system is an asymmetric key encryption algorithm for public key cryptography, which is based on the Diffie-Hellman key exchange. It was described by Taher El-Gamal in 1985. The original public key system proposed by Diffie and Hellman requires interaction of both parties to calculate a common private key. This poses problems if the crypto system should be applied to communication systems where both the parties are not able to interact in reasonable time due to delays in transmission or unavailability of the receiving party. Thus, El-Gamal simplified the Diffie-Hellman key exchange algorithm by introducing a random exponent k. This exponent is a replacement for the private exponent of the receiving entity. Due to this simplification, the algorithm can be used to encrypt in one direction without the necessity of the second party to take actively part. The key advance here is that the algorithm can be used for encryption of electronic messages, which are transmitted by the means of public store and forward services. El-Gamal key generation. In this video, we are going to see about El-Gamal key generation. The basic requirement for a cryptographic system is at least one key for symmetric algorithms and two keys for asymmetric algorithms. The key generation steps are similar to the general scheme. With El-Gamal, only the receiver needs to create a key in advance and publish it. Bob will take the following steps to generate a key pair. Prime and group generation. First, Bob needs to generate a large prime P and the generator G of a multiplicative group, ZP group of the integers modulo P. Private key selection. Now, Bob selects an integer B from the group Z by random and with a constraint 1 is less than or equal to B less than or equal to P minus 2. This will be the private exponent. Public key assembling. From this, we can compute the public key part G power B mod P. The public key of Bob in the El-Gamal crypto system is the triplet, that is P, G, G power B, and the private key is B. Public key publishing. The public key now needs to be published using some dedicated key server or other means so that Alice is able to get hold of it. Encryption procedure. In this video, we are going to see about encryption procedure. To encrypt a message M to Bob, Alice first needs to obtain his public key triplet P-G-G-B from a key server or by receiving it from him via unencrypted electronic mail. There is no security issue involved in this transmission as the only secret part B is sent in G-B. Since the core assumption of the Elgamal cryptosystem says that it is infeasible to compute the discrete logarithm. For the encryption of the plaintext message M, Alice has to follow these steps. Obtain public key. As described above, Alice has to acquire the public key part P-G-G-B of Bob from an official and trusted key server. Prepare M for encoding. Write M as set of integers M1, M2 and so on in the range of 1, set 1 and so on up to P-1. These integers will be encoded one by one. In this step, Alice will select a random exponent k that takes the place of the second party's private exponent in the Diffie-Hellman key exchange. Compute public key. To transmit the random exponent k to Bob, Alice computes G/k mod p and combines it with a ciphertext that shall be sent to Bob. Encrypt the plaintext. In this step, Alice encrypts a message M to the ciphertext C. For this, the iterations over the sets created in step 2 and calculates for each of the mi. Ci is equal to m1 into G/b to the whole power k. The ciphertext C is a set of all Ci with 0 less than I less than or equal to modulus m. The resulting encrypted message C is sent to Bob together with a public key G/k mod p derived from the random private exponent. Even if an attacker would listen to this transmission and in a second step would also acquire the public key part G/b of Bob from a key server, he would still not be able to derive G/b into k, as can be seen from the discrete logarithm problem. Elgamal advises to use a new random k for each of the single message blocks mi. This greatly improves security, as knowledge of one message block mj does not lead the attacker to the knowledge of all other mi. The reason for this ability is that if C1 is equal to M1 into G/b to the whole power k mod p and C2 is equal to M2 into G/b to the whole power k mod p, from knowing only M1, the next part of the message M2 can be calculated by the following formula. M1 by M2 is equal to C1 by C2. Decryption procedure. In this video, we are going to see about decryption procedure. Once received the encrypted message C and the randomized public key G/k, Bob has to use the encryption algorithm to be able to read the plaintext M. This algorithm can be divided in a few single steps. Compute shared key. The Elgamal cryptosystem helped Alice to define a shared secret key without Bob's interaction. This shared key is a combination of Bob's private exponent B and the random exponent k chosen by Alice. The shared key is defined by the following equation. G/k to the power p minus 1 minus b is equal to G/k to the power of minus b is equal to b power minus b into k. Decryption. For each of the ciphertext parts Ci, Bob now computes a plaintext using mi is equal to G/k to the whole power minus b into Ci mod p. After combining all of the mi back to m, he can read the message sent by Alice. Elgamal signatures. In this video, we are going to see about Elgamal signatures. The Elgamal cryptosystem does not only support encryption and decryption, but also the electronically signing of messages M. A signature scheme has three main characteristics: signing process, verification, forgery prevention. A signature in the Elgamal crypto system is the pair R, S with 0 lesser than or equal to R, S less than P minus 1, defined by the equation G power M is congruent to G power A to the whole power R into R power S mod P. The procedure of signing follows similar steps as the encryption procedure. Choose random K belongs to G. Compute R is congruent to G power K mod P. Fill the signature equation from above as G power M is congruent to G power AR GKS mod P and solve it for S using M is congruent to AR plus KS mod P minus 1. This has a solution for S if K is chosen such that GCD of K, P minus 1 is equal to 1. Verification procedure. A signature R, S of a message M is verified as follows. 0 less than R less than P and 0 less than S less than P minus 1. G power H of M is congruent to Y power R into R power S mod P. Correctness. The algorithm is correct in the sense that a signature generated with the signing algorithm will always be accepted by the verifier. The signature generation implies H of M is congruent to XR plus SK mod P minus 1. Hence, Fermat's little theorem implies G power H of M is congruent to G power XR into G power KS, which is congruent to G power X to the whole power R into G power K to the whole power S, which is congruent to Y power R into R power S mod P. Introduction to attacks on Elgamal. In this video, we are going to see about introduction to attacks on Elgamal. The attack applies when encryption is done in a subgroup of ZP group. The simplest form of the Elgamal system encrypts the messages in ZP group for some prime P. Let G be an element of ZP group of order Q. The private key is a number in the range 1 less than or equal to X less than Q. The public key is a tuple set P, G, Y, where Y is equal to G power X mod P. To encrypt a message M belongs to ZP, the original schemes works as follows. Pick a random R in the range 1 less than or equal to X less than Q. Compute U is equal to M into Y power R mod P and V is equal to G power R mod P. The resulting ciphertext is the pair U, V. To speed up the encryption process, one often uses an element G of order much smaller than P. For example, P may be 1024 bits long, while Q is only 512 bits long. In the extreme, one might take Q to be only a 160 bits. Elgamal system in particular are mostly used key management, for example, in the case of email, which encrypts the session key using the recipient's Elgamal key. Session keys are typically short, for example, 128 bits. An attacker can recover the plain text of a given ciphertext using only the public key. Hence, a combination of encryption of a subgroup and encryption of short messages should be done. Subgroup rounding problems. In this video, we are going to see about subgroup rounding problems. Let us assume G belongs to ZP group is an element of order Q where Q is much lesser than P. For assumption, we may take P as 1024 bits long and Q as 512 bits long. Let GQ be the subgroup of ZP group generated by G. Observe that GQ is extremely sparse in ZP group. Only 1 in 2 power 512 elements belongs to GQ. M is also a short message of length much smaller than log base 2 of P by Q. For example, M is a 64 bits long session key. After the random R is chosen, one encrypts a message m by computing u is equal to m plus y power r mod p. That is, we blind the message by adding y power r rather than multiplying by it. The X marks represents elements in GQ. Since m is a relatively small number, encryption of m amounts to picking a random element in GQ and then slightly moving away from it. Assuming the elements of GQ are uniformly distributed in ZP group, the average gap between elements of GQ is much larger than m. Hence, with probability, there is a unique element Z belongs to GQ that is sufficiently close to U. There is also another probability that there will be a unique element Z belongs to GQ satisfying modulus of U minus Z is less than 2 power 64. If we could find Z given U, we could recover M. Additive subgroup rounding. Let Z be an element of GQ and delta an integer satisfying delta less than 2 power m. Given U is equal to Z plus delta mod p. Find Z. When m is sufficiently small, Z is uniquely determined with high probability, assuming GQ is uniformly distributed in ZP. Going back to the original multiplicative Elgamal scheme, we obtain the multiplicative subgroup rounding problem. Multiplicative subgroup rounding. Let Z be an element of GQ and delta an integer satisfying delta less than 2 power m. Given U is equal to Z into delta mod p, find Z. When m is sufficiently small, Z is uniquely determined with high probability, assuming GQ is uniformly distributed in ZP. An efficient solution to either problem would imply that the corresponding plain Elgamal encryption scheme is insecure. All are interested in solutions that run in time order of square root delta, or even better, order of log delta. The reason we refer to these schemes as plain Elgamal is that messages are encrypted as IS. For proper security, one must pre-process the message prior to encryption or modify the encryption mechanism. For example, one could use DHAES. An algorithm for multiplicative subgroup rounding. In this video, we are going to see about an algorithm for multiplicative subgroup rounding. In the given element, U belongs to ZP of the form U is equal to Z into delta mod P, where Z is a random element of GQ and modulus of delta is less than 2 power m. To find delta, assume that m, the length of the message being encrypted, is much smaller than log base 2 of P by Q. Then, with high probability, delta is unique. For example, take P to be 1024 bits long, Q to be 512 bits long, and M to be 64. Suppose delta can be written as delta is equal to delta 1 into delta 2, where both delta 1 and delta 2 are m by 2 bits each. To find delta from U in time, order of 2 power m by 2. Observe that U is equal to Z into delta is equal to Z into delta 1 into delta 2 mod P. Dividing by delta 1 and raising both sides to the power of Q yields U by delta 1 to the power Q is equal to Z power Q into delta 2 power Q is equal to delta 2 power Q mod P. We can now build a table of size 2 power m by 2 containing the values delta 2 power q mod p for all delta q is equal to 0 and so on up to 2 power m by 2. Then, for each delta 1 is equal to 0 and so on up to 2 power m by 2, we check whether u power q by delta 1 power q mod p is present in the table. If so, then delta is equal to delta 1 into delta 2 is a candidate value for delta. Assuming delta is unique, there will only be one such candidate. The algorithm above requires 2 power m by 2 plus 1 modular exponentiations and order of 2 power m by 2 space. Hence, when the system is used to encrypt a 64-bit session key, the algorithm requires on the order of 8 billion exponentiations. Far less than the time to compute discrete log in ZP group. This attack works only when delta factors into a product of two integers, each approximately m by 2 bits long, and these factors need not be prime. When m is equal to 64, the density of such delta is approximately 8%. This is a heuristic estimate. Hence, roughly 1 out of 12 messages can be decrypted using the algorithm. Semantic security. In this video, we are going to see about semantic security. In cryptography, a crypto system is semantically secure if any probabilistic polynomial time algorithm PPTA that is given the ciphertext of a certain message M taken from any distribution of messages and the message's length cannot determine any partial information on the message with probability non-negligibly higher than all other PPTAs that only have access to the message length. Symmetric key encryption scheme, finite case. A symmetric key encryption scheme with key length k, plain text length m, and ciphertext length c is a pair of probabilistic algorithms E and C, DEC such that E and C encryption set 0, 1 per k into set 0, 1 per m tends to 0, 1 per c. Decryption DEC set 0, 1 per k into 0, 1 per c tends to 0, 1 per m. And for every key k belongs to set 0, 1 per k and every message m, P of decryption DEC of k, encryption ENC of k, m is equal to m, which is equal to 1, where the probability is taken over the randomness of the algorithms. Symmetric key encryption scheme, variable key length case. A symmetric key encryption scheme with variable key length is a pair of polynomial time probabilistic algorithms, encryption, decryption, that is ENC, DEC, and a function m of k is greater than k, such that for every security parameter k, for every key k belongs to set 0, 1 per k and every message m belongs to 0, 1 per m of k. P of decryption DEC of k, encryption ENC of k, m is equal to m, which is equal to 1. Semantic security concrete definition. An encryption scheme, encryption, decryption, ENC, DEC is T0 belongs to semantically secure if for every distribution x over messages, every functions L set 0, 1 per 1 tends to set 0, 1 group and F set 0, 1 per m tends to set 0, 1 group of arbitrary complexity and every function a of complexity Ta is lesser than or equal to t, there is a function a dash of complexity lesser than or equal to Ta plus O such that P of A of encryption ENC of k, m, I of m is equal to f of m minus P of A dash of I of m is equal to f of m is lesser than or equal to epsilon. Consider as before of t is equal to 2 power 80 and epsilon is equal to 2 power minus 60, and suppose O is quite small so that a computation of complexity O can be performed in a few seconds or less. And notice how the above definition captures the previous informal discussion. Semantic security implies message indistinguishability. If encryption ENC, decryption DEC is T, O, epsilon semantically secure, then it is T, 2 epsilon message indistinguishable. Note that semantic security implies message indistinguishability regardless of the overhead parameter O. Proof: we prove that if encryption ENC, decryption DEC is not T, 2 epsilon message indistinguishable, then it is not T, O, epsilon semantically secure regardless of how large is O. If encryption ENC, decryption DEC is not T, 2 epsilon message indistinguishable, then there are two messages M0, M1 and an algorithm T of complexity less than or equal to T such that P of T of encryption ENC of K, M1 is equal to 1 minus P of T of encryption of K, M0 is equal to 1 greater than 2 epsilon. Pick a bit B uniformly at random in set 0, 1, then we have P of T of encryption ENC of K, MB is equal to B greater than 1 by 2 plus epsilon. And now take A to be T, X to be the distribution MB for a random B, and define f of MB is equal to B and I of M to be empty. Then P of A of I of M, encryption ENC of K, M is equal to f of M greater than 1 by 2 plus epsilon. On the other hand, for every A dash regardless of complexity, and so we contradict semantic security. P of A dash of I of M, encryption of K, M is equal to f of M, which is equal to 1 by 2. Message indistinguishability implies semantic security. If encryption ENC, decryption DEC is T, epsilon message indistinguishable and ENC has complexity less than or equal to P, then encryption ENC, decryption DEC is T minus LF, P, epsilon semantically secure, where LF is the maximum length of f of M over M belongs to 0, 1 power M. Proof: fix a distribution X, an information function L, a goal function F, and a crypto-analytic algorithm A of complexity LF into X is less than or equal to T. Take A dash of I of M is equal to A into I of M, encryption ENC of K, 0, so that the complexity of A dash is equal to the complexity of A plus the complexity of encryption ENC. For every message M, we have P of A of I of M, encryption ENC of K, M is equal to f of M, which is equal to P of A of I of M, encryption ENC of K, 0 is equal to f of M plus epsilon. Otherwise, defining T of C is equal to 1 bidirectionally equivalent to A of I of M, C is equal to f of M would contradict the indistinguishability. Averaging over M in X. M is proportional to X, K belongs to the set 0, 1 to the power N. P of A of I of M, encryption ENC of K, M is equal to f of M less than or equal to m proportional to x, comma k belongs to the set 0, comma 1 power n, p of a of I of m, comma encryption enc of k, comma 0 is equal to f of m plus epsilon. And also m proportional to x, k belongs to the set 0, comma 1 power n, p of a of I of m, comma encryption enc of k, comma m is equal to f of m less than or equal to m proportional to x, k belongs to the set 0, comma 1 power n, p of a dash of I, comma m is equal to f of m plus epsilon. Semantic security asymptotic definition. An encryption scheme, encryption ENC, decryption DEC is semantically secure if for every polynomial p there exists a polynomial q and a negligible function nu such that encryption ENC, decryption DEC is p of k, q of k, nu of k semantically secure for all sufficiently large k. Chosen ciphertext security. In this video, we are going to see about chosen ciphertext security. A chosen ciphertext attack (CCA) is an attack model for cryptanalysis in which the cryptanalyst gathers information, at least in part, by choosing a ciphertext and obtaining its decryption under an unknown key. In the attack, an adversary has a chance to enter one or more known ciphertexts into the system and obtain the resulting plaintext. An encryption GEN, E, D is said to be T, epsilon. CCA secure if it's valid for every E, D is equal to GEN of 1 power n, D of E of x is equal to x. And for every T time A, if we consider the following: E, D is equivalent to RG of 1 power n. A gets as input E. A gets access to black boxes for E of dot redundant and DD of dot. A chooses x1, x2. Sender chooses I tends to R into set 1, 2 and gives AY is equal to EE of XI. A gets more access to black boxes for EE of dot redundant and DD of dot but is restricted not to ask Y to the decryption box. More formally, A gets access to the following function D of dot instead of DD of dot. DD dash of Y dash is equal to DD of Y dash into Y dash is not equal to Y. Y dash is equal to Y. Perpendicularity is a symbol that signifies failure or invalid input. A outputs J belongs to the set 1, 2. A is successful if J is equal to I. The scheme is T, epsilon. CCA secure if the probability that A is successful is at most 1 by 2 plus epsilon. CPA secure scheme in the random oracle model. In this video, we are going to see about CPA secure scheme in the random oracle model. One advantage of this scheme over the hardcore bit-based scheme is that it will have shorter ciphertexts. To encrypt n bits will need 3n bits as opposed to 2n square in the previous bit-by-bit scheme. The main advantage of concern is able to generalize it to a CCA secure encryption scheme. A CPA secure scheme. Let G of set 0, 1 to the power n tends to 0, 1 to the power n be a random oracle and set F, F inverse be collection of trapdoor permutations. The public key of the scheme will be F of dot while the private key be F inverse. To encrypt X belongs to set 0, 1 power n, choose R tends to R to set 0, 1 power n and compute F of R, G of R addition of X To decrypt y, z, compute r is equal to f inverse of y and let x is equal to r addition of z. Theorem 1. Proof. For public key encryption, the encryption oracle is redundant, and so CPA security means that an adversary A that gets as input the encryption key f of dot in our case cannot tell apart e of x power 1 and e of x square for every x power 1, x square. However, in the random oracle model, need to give A also access to the random oracle g of dot. We denote the ciphertext A gets as challenged by Y group, Z group, where Y group is equal to F of R group and Z group is equal to G of R group addition of X group. CCA secure encryption. In this video, we are going to see about CCA secure encryption. First, note that if we have one random oracle, we can have many independent oracles. Just have gi of x is equal to g of I, o, x. We will use two independent random oracles g, h in the next scheme. Let g, h the set 0, 1 power n tends to 0, 1 power n be two independent random oracles and set f, f inverse be collection of trapdoor permutations. The public key of the scheme will be f of dot while the private key be f inverse. To encrypt x belongs to set 0, 1 power n, choose r tends to r the set 0, 1 power n and compute f of r, g of r addition of x, h of x, r. To decrypt y, z, w, compute r is equal to f inverse of y and let x is equal to r addition of z. Then check that w is equal to h of x, r. If so, then return x, otherwise return perpendicularity. Theorem 2. Proof. Let A be an algorithm in a CCA attack against the scheme. Again, denote by Y group, Z group, W group the challenge ciphertext A gets where Y group is equal to F of R group, Z group is equal to G of R group addition of X group and W group is equal to H of X group, R group. Since H is a random oracle, we can assume that throughout the attack no one, that is the sender, receiver or A, will ever find the two pairs X R and X dash R dash such that X underscore R 6 is equal to X dash dot R dash, but H of X, R is equal to H of X dash, R dash. Thus, at each step I of the attack and for every string W belongs to set 0, 1 power n, we can define Hi inverse of W in the following way. If the oracle H was queried before with some X, R and returned W, then Hi inverse of W is equal to X, R. Otherwise, Hi of inverse of W is equal to perpendicularity. We also observe that a pair X, R completely determines the ciphertext Y, Z, W, that is a function of X and R, and also that Y, Z completely determine X and R. Provably secure schemes. In this video, we are going to see about provably secure schemes. Provably security refers to any type or level of security that can be proven. It is used in different ways by different fields. Usually, this refers to mathematical proofs which are common in cryptography. In such a proof, the capabilities of the attacker are defined by an adversarial model, also referred to as attacker model. The aim of the proof is to show that the attacker must solve the underlying hot problem in order to break the security of the model system. Generally, A security proof attempts to show how difficult breaking a cryptographic scheme. The main difference between proving the security in the signature setting and the encryption setting is deciding what is breaking the scheme. There are several lines of research in provable security. One is to establish the correct definition of security for a given intuitively understood task. Another is to suggest constructions and proofs based on general assumptions as much as possible, for instance, the existence of a one-way function.